Hey there, let's talk about the rates of nuclear decay and radiometric dating. As we talked about earlier this year, radioactive decay follows first-order kinetics. This means we can write a familiar rate law. Rate equals k times a to the first. When we're working with radioactive samples, they're often not solutions, so talking about concentration doesn't make sense in the same way. Instead, we're going to rephrase this equation as rate equals k times n to the first, where n is the number of radioactive nuclei that are present in a sample. The rate of decay for a radioactive sample is known as its activity and has units of disintegrations per second, or becquerel. An older unit for activity is the Curie, which is 3.7 times 10 to the 10th disintegrations per second. This happens to be the decay rate for 1 gram of radium, which is one of the isotopes and one of the elements that the Curies worked with and discovered. Now, recall that for a first-order process, the half-life is independent of sample size and can be determined directly from the rate constant. So if we take 0.693 divided by k, we get our half-life. It is worth noting that for a radioactive decay process, the rate constant and half-life are actually unaffected by external conditions, things like pressure, temperature, or the chemical compound that the material is a part of. Also remember that when you graph how the number of particles changes over time, you get a characteristic curve where the amount of time it takes to decrease the number of particles by half is constant. Remember to be on the lookout for that particular curve as a signal that you have a first-order process. Now, also remembering your kinetics, you will know that we have integrated rate equations where we can relate how the number of particles change over time. So for a first-order reaction, the natural log of the number of particles at any particular time, nt, is going to be equal to the natural log of the number of particles initially minus kt. And this can be rearranged using log rules into a ratio form, where the natural log of the ratio of the number of particles at time t over the initial time is equal to minus kt. And this last one's going to be helpful when we're working with our radioactive decay processes. As both the mass of a particular radioisotope and its activity, the number of disintegrations per second, is proportional to the number of the radioactive nuclei present in a sample, we can substitute either mass or activity values for n when we're using this equation. Because radioactive decay is a first-order process, we can use half-life information and the measured amounts of radionuclei present in a sample to determine the age of a material. We call this process radiometric dating. This nuclear clock is regularly used to determine the age of rocks and archaeological sites. We simply pick a radioactive element whose half-life is appropriate to the situation and that's found in the material. There are a whole host of different elements that are used for this application: uranium-238, potassium-40, carbon-14, and many others. When carbon-14 is being used, we call it radiocarbon dating, and it has a special place because it is so important to archaeology. Carbon-14 is formed when neutrons generated by cosmic rays in the upper atmosphere convert nitrogen-14 into carbon-14, which has a half-life of about 5,700 years. The carbon-14 gets incorporated into carbon dioxide and from there into plants in the food chain. The amount of carbon-14 found in living plants and animals is identical to that in the atmosphere as long as the organism is alive. But once it dies, new carbon-14 is no longer ingested to replace what is lost through radioactive decay, and that ratio of carbon-14 to carbon-12 begins to change. So if an object has a ratio of carbon-14 to carbon-12 that's about half that of the atmosphere, then it died about 5,700 years ago, one half-life ago. We can use the integrated rate equations on the previous page to determine specific ages, just plugging in that ratio for nt and n naught. This method is super useful for dating objects younger than about 50,000 years old. But older than that, and the amount of carbon-14 is just too small to measure accurately, and radiocarbon dating is just not useful. For objects that are older than about 50,000 years old, we need to find different isotopes that have longer half-lives. Let's take a look at a couple of examples. If we have a wooden object, perhaps from an archaeological dig, and it has a carbon-14 activity of 9.6 disintegrations per second, if the activity of a piece of fresh wood is 15.2 disintegrations per second, what's the age of the wood, given that the half-life of carbon-14 is 5,700 years? We have our integrated rate equation and we have a half-life. So that's going to allow us to find a value for K for carbon-14. And that's 1.2 times 10 to the negative fourth. So I can put that in for K. I can use the 15 or the 9.6 disintegrations per second as the activity of my object, and not that initial activity would be the 15.2 because that's for fresh wood. So I can plug those values in. And when I solve for T, I get a value of 3,829 years. So we'll just call that about 3,800 years old. Again, radiocarbon dating is great up to things that are about 50,000 years old. If things are older than that, we need a different isotope. So let's take a look at a second example. We have a rock, contains 0.257 milligrams of lead-206 for every milligram of uranium-238. Lead-206 is the decay product of uranium-238, which happens to have a half-life of 4.5 times 10 to the 9th years. We can figure out the age of the rock using our integrated rate equation. So I've got it written here. The natural log of the number of particles at time t over the initial number of particles is minus kt. Okay, so we need K. We have a half-life. We can figure out K. Remember that your half-life is 0.693 over K, and this is 4.5 times 10 to the 9th years. So we can just rearrange and solve for K. 1.5 times 10 to the negative 10th inverse years for your units on K. Cool. Now we just need to know our values for N. Remember, you can use mass because that's proportional to the number of particles. So we know the mass at time t. It's 1 milligram of uranium-238 remaining in the rock. We just need to know how much there was to start with when this rock formed. Okay, well, the original mass of the uranium-238 will be the milligram that remains plus the amount that has decayed away. Now that 0.257 milligrams for the lead-206 weighs less than the original uranium did. So we're going to take those mass numbers into consideration and multiply the mass that's decayed away by that ratio to figure out how much we started with. And this turns out to be 1.297 milligrams. So now we know the rate constant, we know the amount that we have at time t, which is 1 milligram, and we know the initial amount of the uranium in the milligrams that was present in the rock. We can just plug the numbers in. When you plug the numbers in and solve for it, you get 1.7 times 10 to the 9th years. So that's the age of the rock.